We know how to find a percentage increase of an amount using a percentage multiplier. If you want to increase something by 12%, you multiply by 1.12. We also know how to calculate the amount of interest we have at the end of a certain number of years. For instance, if you have a 12% interest rate and you wait for 5 years, the overall effect of those 12% increases will be equivalent to multiplying by 1.12 to the power 5. What we're going to look at today is what happens when interest is not simply calculated and paid every year, but calculated and paid every month. That may not seem like much of a difference, but banks and credit card companies like to quote the interest rate as an annual figure rather than a monthly figure or weekly figure, depending on how they compound things, which means we have something called the nominal interest rate. If they're going to pay you 1% every month, they will usually state that it is a 12% per annum interest rate. Now, 1% every month has a slightly different effect to 12% once. If you apply a 1% interest rate 12 times, the overall effect is more like a 12.7% interest rate. Effective rate of interest is going to talk about how we can calculate that interest rate, the interest rate you actually get paid when you know the nominal interest rate. To start with though, we're going to try these 3 questions which break down how to calculate the actual amount of money you end up with. So we'll make sense of the compounding period, the length of time over which interest is calculated, and we'll see how we can work out values and check that they make sense. In the first question, we have £3,500 invested at 4%, but that's the nominal interest rate. In order to calculate how much the actual interest paid each week would be, we have to divide 4% by the 52 weeks that are in a year. It tells us that interest is compounded weekly, so we know we have to split into 52 equal pieces and treat each separate week as another compounding period. The other thing we need to do is work out how many weeks we're dealing with. It's 2 years, which means 2 lots of 52 weeks. These are the 2 different aspects you have to get right. If you forget to change the number of compounding periods from 2 to 104, or you forget to change the interest rate from 4% to 0.07%, either of those will significantly affect the size of your answer. In one case, it might make your answer much too small, in another case, much too big. So hopefully in both situations, you'll notice that you've got the answer wrong, and you'll be able to go back and check what went wrong. Once you know how many weeks there are, and you know what the percentage increase each week would be, you can use the same multiplier method we've used before. For a 0.07% increase, you need to convert 0.07% into a decimal. Got to be careful with this because 0.07 already looks like a decimal multiplier, but that will be the decimal multiplier that goes with 7%. We have a percentage which is much smaller even than 1%. It's 0.07%, which means 0.0007 will be the corresponding multiplier. A good tip here is to divide the percentage multiplier for the 4%, in other words 0.04, by 52. Get that number on your calculator. It'll already be 0.000769. Then you can add 1 and you'll have the percentage multiplier you need. At that point, you multiply by that number to the power of the number of compounding periods. For the second question, we have a fixed amount at the beginning, £2,000. We have a nominal interest rate, this time of slightly less, 3%, and we're compounding semi-annually. That means every 6 months. Occasionally you'll hear the phrase biannually. Semi-annually means every half year. Biannually means twice a year, which is exactly the same thing. To avoid confusion, I will always add an extra statement, for instance, in this case, every 6 months, to make it clear what's going on. There are no cases I know of where people pay interest once every 2 years. Once every year is about as infrequent as it ever gets. Now this question is slightly different in that instead of asking you how much you will have, it asks how much interest you can expect to earn. So we still need to calculate in exactly the same way that we've done before, but there's an additional extra step at the end, which it's very easy to miss off. The first time I did these questions, the thing I missed off here, even though I wrote the question, was I calculated the total amount, but I forgot to work out how much of that was the additional interest I'd earned. So to start out, you work out how many compounding periods there are. We're waiting for 4 years, but we get paid twice every year, which means there are 8 compounding periods altogether. The other thing is to adjust the interest rate. 3% per year gets converted into 1.5% every 6 months. So we'll use 1.5% to find our percentage multiplier. 1.5% is 0.015. So 1.015 to the power 8 will apply a 1.5% interest rate 8 times. Once you know how much money you have in the bank, you can work out how much interest you've been paid. For the third question, one thing that's different about this one, we don't know how much money we have at the beginning. We borrow some money and we know the nominal interest rate per annum, we know that it's compounded monthly, and we know that we've waited 5 years and now we owe more than £1,000. The question is, what's the least amount of money I could have borrowed at the beginning in order for it to have turned into more than 1,000 at this point? A good way to think of this is imagine it's exactly 1,000 now and work out how much it would have been before the 5 years. But we can still set it up in exactly the same way. We can start it out by thinking about what 30% should be if we split it into 12 equal pieces, because it's 30% per annum and we want to compound monthly, that is 12 times in a year. So we can do 30 divided by 12. We also need to consider the fact that we have 5 years and each year has 12 months in it. So the total number of months is 60, and we're going to have a 2.5% increase every month. So whatever the original amount was that we had, we might call it P for the principal amount, we would multiply that by the percentage multiplier for 2.5%, 1.025. And we do that 60 times because there are 60 months. Now, I've written this in the form of an equation, but hopefully you can see there's only one key step in here. The number I don't know, the one I want to find out, the money I borrowed initially, if we multiply that by this important number, 1.025 to the power 60, we should get the answer of 1,000. But that means if we start with 1,000 and we divide by our percentage multiplier term, we should end up with the correct value. And that's what the £227.28 must be. In fact, you can check fairly quickly that £227 is approximately correct. Even if you ignore the complications of the compounding period, you can simply apply a 30% increase 5 times. You can do 227 times 1.3 to the power of 5, and it should be approximately what we're getting here. I come out with £842. The discrepancy comes from the fact that I've ignored the fact that it's being compounded monthly when I work backwards to check my answer. And that has a significant effect when we're talking about a large enough interest rate and a long enough run. But roughly speaking, 227 seems like a plausible result. It's going to grow quite a lot, even in 5 years, if the interest rate is as high as 30% per annum. So now we get on to the idea of effective rate of interest. You'll notice, unlike the last set of questions, none of these mention how much money you're investing. That's because it shouldn't be relevant to the question. If a bank account has a good rate of interest, then it's better than a bank account that has a worse rate of interest. And it doesn't matter if you're saving 100 or 1,000 or £100,000. So your choices are 15.6% interest applied every single year, or half that, 7.8%, applied every 6 months. So you get it twice as often, but it's only half the size. Or you get a quarter of the interest, 3.9%, but it gets applied every quarter. That means a quarter of a year, so every 3 months. And again, it'll happen 4 times during the year. We can have 1.3% monthly, or about 0.3% every week, which is 52 times during the year. Now, if we look at what happens when we apply these things, think about the overall effect. The first one, over the course of a year, will be to increase the amount of money you have by 15.6%. If you invest 1,000, you end up with £1,156. So we can see that for the first one. We can also do a similar thing for the second one. But if it's a 7.8% increase twice, we multiply by 1.078 squared. And you find that we do slightly better. about £6 better. If we go to option C, we do a little better again. Option D is even better, and if you apply your interest weekly, you do even better still. But you might notice there's not a massive difference between them. There is an improvement when you apply interest more and more frequently, but even if you apply interest daily or every hour or even every second, there is a limit that you can't get beyond. This doesn't increase without limit. You end up approaching a point where you don't get any extra benefit, or at least the benefit is so small that it's less than a fraction of a penny. Now, instead of thinking about £1,000, we can think in terms of the actual percentage multiplier itself. The effective rate of interest for the first one is exactly 15.6% because the compounding period is 1 year. But for the second one, we would do 1.078 squared and we get 16.2%. If you do 1.078 squared, the value you get is 1.16208, which is equivalent to an interest rate of 16.208%. So that's what we call the effective rate of interest. It's the equivalent of having 16.208% applied at the end of the year. In part C, if you calculate the size of the percentage multiplier and convert it into a percentage increase, we can see it's a 16.537% increase. For part D, 1.013 to the 12, that's equivalent to 16.765% increase, and the final one is 16.855. Remember what these mean. This is essentially how much you would need a bank account to be paying if they were only compounding every year. This tells you the advantage you get by having monthly or weekly compounding periods. If you're curious and you're thinking about the maximum possible interest you could make, well, even if you compound as often as you like, even if you break it down to every millisecond, there is a limit, and the limit involves the mathematical constant e, which is about 2.7 something. And in this case, the maximum you can reach is e to the power of the original percentage, e to the power of 0.156, which is £1,168.83. You'll notice that's nearly 30 pence better than applying interest weekly. That's the only improvement you can make at that point. So there's not a huge difference, especially when you get down to small compounding periods. If you need more practice with percentages in general, there's a percentage change practice spreadsheet that you can find on LearnZone. There is also an effective rate of interest spreadsheet. It's bundled with the net present value spreadsheet, which we'll get to in a later lesson. But the effective rate of interest spreadsheet allows you to mess with the nominal annual interest rate. We've got 15.6% in here, just like the example before. And you can see what happens if you compound at different lengths. The key idea here is that you have a smaller interest rate applied, but you have it applied more frequently. And the overall effect is that you get slightly more money if you apply the interest more often. The effective rate is essentially the interest rate that additional compounding represents. Now let's look at what a question will involve. We'll see how to calculate the effective rate of interest. You should recognize these numbers from before. If you have a 4% increase per annum compounded weekly, what that means is we're dealing with 52 compounding periods during the year. If you add up all of the interest rates from the 52 separate instances, you should get 4%. So we divide 4% by 52 and we find the actual interest rate which is applied every month. 4% divided by 52 gives us the 0.0769% per week. And if we raise that to the power of 52, it gives us the percentage multiplier that corresponds to that percentage increase that many times. Because it's equivalent to 104.0795%, we say the effective rate of interest is that 4.0795%. Remember, a percentage increase will be 100% of something and an additional something else percent of it. And with a 4.0795% interest, you have a 4.0795% increase. For the next one, you have 3% per annum, but it's compounded semi-annually. Because the compounding is every 6 months, you get 2 compounding periods in a year, and you will have half the interest rate. So we divide the interest rate by the 2 compounding periods, and we apply that 1.5% that results twice. We multiply by 1.015 twice, which means we're multiplying by 1.015 squared. And if you calculate 1.015 squared, we get 1.030225. That's equivalent to a 3.0225% interest rate. You can see that these will be similar to the nominal interest rate in every case. 4 became 4.08% roughly, and 3 became 3.02% roughly. There's not a huge change, but there is a small improvement. Question 3 is a bit more involved. There are 2 different banks. One of them offers you 8% on a loan, and the other 8.5%. Remember, if you're borrowing money, you want the interest rate to be as low as possible, because interest always tells you how an amount is growing. But if the amount of money is money that you have borrowed, you don't want it to grow as fast as if it's money that you're saving. So 8% seems better than 8.5%. But the 8% loan is compounded daily, 365 times a year, whereas the 8.5% loan is compounded quarterly, just 4 times a year. So in order to do a proper comparison and decide whether the increased compounding makes the 8% bank worse than the 8.5% bank, we'll have to do the calculations. First, split the 8% into 365 pieces and apply them 365 times. And then the 8.5%, share it into 4 pieces and apply the percentage multiplier 4 times. Now you'll notice I'm writing this slightly differently to the ones I've done before. This is a formula that will be on your formula sheet. It's one that it's important to make sense of and understand. So by the time you get to the exam, it shouldn't strictly be necessary for you to read the formula, although you might still want to, because you'll understand why it works. Look closely at what's happening inside each term. We have 0.08, the original interest rate for the entire year, divided by 365, the number of compounding periods, and then we add that to 1. That converts the number which is the interest rate multiplier for a single day into the overall increase, 100 and something percent. When you raise that to the power of 365, you're applying it 365 times for an entire year. And the overall effect is 1.083 something, which means 8.3 something effective rate of interest. The next one is an 8.5% interest rate, but we divide that by 4 to work out the interest which will be paid each quarter. When you add 1, you turn it into a percentage multiplier that will increase by that percentage, and then when you raise to the power 4, you apply that 4 times. The overall effect is 8.77%. So the compounding that's happened for both banks has slightly increased the interest rate for both banks. But for the first one, it increased up to 8.33, and for the second one, up to 8.77. So the best choice is going to be Bank A still. Despite the additional compounding, the 0.5% discrepancy between them was more than enough to compensate for that. Although 8.1% would be worse than 8% compounded daily, 8.33% is effectively what 8% compounded daily is the same as. So we'd be better off with Bank A.